In this video, we'll talk about some of the basic Prolog operators. Let's start with equality. So open up a Prolog window. So equality is just the operation we've learned before. It's just the equals sign. And it's true if the two terms around the equal sign can unify. So x equals y. It's true if x gets the value of y. And we've already seen the unification rules. So for example, integers will unify with themselves. Atoms like hello will unify with themselves if they're identical. And compound terms will unify under the condition that they have the same functor, the same arity, and each one of their individual arguments or their terms in the tuple can unify one-to-one as well. Right, so we've already looked through all of that, so that's the basic idea behind equality. Will these two things unify? There's also a not equals operation, so I could say something like x equals 3, y equals 4, and then x does not equal y. And that's true under those binding conditions. Now the not equals succeeds if equality or if unification fails. So it's essentially the same as saying x equals 3, y equals 4, and not x equals y. Means pretty much the same thing. Now it's worth mentioning there's also a double equals operator that does a similar thing. It says are these two things equal, but it doesn't attempt to unify them. So if I said something like y double equals 3, that comes up false because y doesn't have the value 3. Y is an unbound variable. On the other hand, if I just say y single equals 3, that's true with the unification that y gets the value 3. All right, so if I said x equals 5 and then x double equals 5, that becomes true because x got the value 5 in the first step, and then we ask, does it have the value? We can similarly ask x equals 5 and then x does not have the value 4, and that becomes true because, again, x has the value 5 here. So this does the same thing. This fails if the comparison succeeds, and succeeds if the comparison fails, but does not attempt to do any unification. So this operation here doesn't say give the value of 5 to x, just says does it already have the value? If so, great. If not, false. Okay. So in addition to equality, we have a number of comparison operators. These are pretty much the standard comparisons, so I could ask, is 4 less than 10? And that's true because of math. I could ask, is 5 greater than or equal to 2? And that, again, is true. The only one that's worth mentioning in terms of something different is the less than or equal to sign. Looks a little bit strange. I could say 1 is equal to or less than 10. And that's true. It's just the order of the two symbols here, the equals and the chevron, switch in this case. The way to remember that is that the arrow always points at the equals in Prolog. Okay. A couple things to mention about these comparison operators, though. First off, they only work on numbers. So I can't, for example, say is A less than B. It gets all kinds of errors because we can't actually do that comparison. Abort. And they require instantiated values. So if I said something like, is x greater than, let's just get this space here, is x greater than 5? Well, it doesn't know because x doesn't have a value. So what are we comparing to 5 for truth or falseness? So arguments are not sufficiently instantiated, so we got an empty variable and the value 5. We can't do a comparison. Okay. On the other hand, if I said x equals 7 and now is x greater than 5, that's just true because x has the value 7. Okay, so equality, comparison operators. Another useful type of operation in Prolog is a bunch of type checking predicates. So these are things like number, for example. Number 42 returns true because 42 is a number. On the other hand, if I asked number, the word 3, that's false because that's an atom, not a number. We could ask about variables. So var of x is true if x is an unbound variable. So var of x now comes up false. Okay, so this only works if x has no value. If we give x a value and then ask is x still a variable, var becomes false. Next we have atom, which returns true if the term in the argument here is just an atom type. So something like A. On the other hand, if I used something like atom 3, 3 is not an atom because atoms are just these lowercase symbols. So atom 3 comes false, and similarly using a compound term like F1, 2, 3, that's also false because that's a compound term, not an atom. Right. One last one here is atomic, which is similar to atom, but with an IC at the end. An atomic is true of anything that is not a compound term and not an unbound variable. So atomic A is true. Atomic 3 is also true, but something that isn't true, for example, would be atomic F of 3. That's false because this is a compound term, so it wouldn't match to something that's something that's atomic. So the difference between atom and atomic is that atom is very specifically the type of term that refers to symbols that start with a lowercase letter. Scroll up in the notes to see the definition of an atom and a bunch of examples, where atomic refers to an entire class of terms that can't be subdivided any further. Right? With a compound term, we can talk about the functor or the individual terms inside it. With a variable, we can distinguish between the symbol and its value. But atomic just says these things are essentially self-evaluating. They are what they look like. Okay. Now, it's worth mentioning that if we have a bound variable, the type of that variable is the value that's bound inside it. So if I say x equals 3, var of x is false. But if I say x is 3, I can ask number x, and that's true. X becomes a number in that case. Okay. So once we've bound a variable, they take on the type of their value. Now, let's talk about arithmetic next. Arithmetic in Prolog is it's a bit interesting. Again, Prolog is more designed for symbolic manipulation, not so much for doing math operators, but SWI Prolog supports all of that. One thing to mention that's very important to be cognizant of is that math operators don't cause arithmetic to be performed. So if I say x equals 3 plus 4, this doesn't mean x gets the value 7. It means x gets 3 plus 4. Okay? X now gets unified with the compound term 3 plus 4. And it's worth mentioning this is essentially just this is just a compound term where the relation is plus and the tuple is 3 and 4, but it gets special design because it's arithmetic. We can actually say in a more standard format, x is plus 3 comma 4. Okay, and you can see it actually just translates it to the infix notation, but this would be the more standard version of what a compound term looks like. They mean the same thing. Now, on its own, these things don't do any math, right? It's the same thing as if we had said x equals owns John book, right? That just means x now has that value for the duration of that query. That's true if x gets this compound term as its value. If we want to perform some actual arithmetic, though, we can use what's known as the is operator. So, yeah, something like 7 equals, let's do 7 is, x is 3 plus 4. So with the is operator, it says evaluate the thing on the right-hand side. So 3 plus 4, it evaluates the arithmetic down to 7, and then does the unification with x. Okay, so it's 2 steps. Is says evaluate, and then unify. Right, so similarly, we could ask 7 equals 3 plus 4. And that's false because 7 isn't the symbols 3 plus 4, but if we want to know 7 has the same value as evaluating 3 plus 4, we could say 7 is 3 plus 4. Right, so that does the evaluation and then unifies, and we get true. Okay. Similarly, we could say something like y is 3 plus 4 divided by 2. And here we get 5. And the reason we get 5 and not 3.5 is because Bedmas, or precedence rules. So the first thing that happens is 4 divided by 2, which gives us 2, and then 3 plus that. So standard order of precedence rules apply. Brackets, exponents, division, multiplication, addition, subtraction. All right. Now, like with comparison, if we want to do some arithmetic, we have to make sure that our variables have values. So if I say something like y equals 3, z equals 4, and then x is y times z, we can walk through this. Y unifies with 3 because it's an unbound variable, so now y has the value 3. And then z will unify with 4, where z now has the value 4. So now when we ask x is y times z, it first evaluates this right-hand side, so we get 3 times 4, 12, and then it unifies, so x equals 12. Okay, so y gets its value, z gets its value, and then it does the math. That's all well and good, but if I did this in a different order, if I said x is y times z, and then y equals 3, z equals 4, ideally this should work because Prolog's supposed to be declarative, so if we take all these facts as order agnostic, we just say if all this information is true, there's one way for it to be true, and that's essentially the way we just saw. That would be great, but Prolog does have some order in mind, so it tries to evaluate the first term of this clause first. So x is y times z. Y and z don't have values yet, though, so when it goes to do that multiplication, they're uninstantiated variables. You can't multiply two uninstantiated variables, and we get this error. Arguments are not sufficiently instantiated. All right, so if we want to do some arithmetic, we have to make sure that we use the is operator to actually call the evaluation of that arithmetic, and we have to make sure that our arguments are fully instantiated. Now there's another operation that's similar to is, so let's just show you a couple of steps here. So we can say 5 plus 2 equals 4 plus 3. And this is going to be false because 5 plus 2 is just the symbols 5 plus 2, and 4 plus 3 is just the symbols 4 plus 3. So that gives us false. We could say 5 plus 2 is 4 plus 3. And that says evaluate the right-hand side, so we get 7, and then try to unify. So 5 plus 2 equals 7. And again, that's false because 5 plus 2 is a bunch of symbols, 7 is just the number, so we have a compound term unifying with an atom, and we get false. Okay, so is only evaluates the right-hand side. If we want to evaluate both sides, we could use this operator here, equals, colon, equals, and then 4 plus 3. This says evaluate both the left and the right, and then attempt to unify. So 5 plus 2, we evaluate that down to 7. 4 plus 3, we evaluate that down to 7. And then we get the unification of 7 equals 7, which is obviously true. Okay. And worth pointing out, we can also use the infix notation or prefix notation. So if you prefer, you can say 5 comma 2 is equal to 5 plus 2. And that's true as well. All right, so a couple of practice problems here. Again, these are better when there's a room full of people, but I'll walk through them anyways. There's still a lot of useful knowledge in here. So first example here is x equals 3, comma, y is x times 2, comma, y is greater than or equal to x. Now again, I recommend you pause the video at each one of these. Try and figure these out for yourself. Is this gonna be true or false? If it's true, what will the unifier be? If it's false, why is it false? So find where the unification fails, or where the evaluation fails. That said, I'm now going to walk through it. Okay, so x equals 3, that's an easy unification. And we come to the next step, y is x times 2. Since x has a value, x equals 3, we get 3 times 2. So that's 6, and then y is 6. So y gets unified with the value 6. Now we ask, 6 is greater than or equal to 3. Obviously that's true. And we get true under the conditions that x is 3 and y is 6. Okay. Z is 3 minus 4 times negative 2. This one I'm actually just going to run. So we're expecting the answer here to be multiplication first. So 4 times negative 2 should be negative 8. And then 3 minus that should be negative 5. But if we run this, we actually get a syntax error. It's actually a bit of a Prolog oddity here. The issue is these two symbols here, times minus right next to each other. Prolog can't understand how that's supposed to evaluate. It actually complains there, which is strange. But the error is actually happening here. Yeah, and the way to fix this is just to use brackets. So z is 3 minus 4 times. To specify negative 2, you just wrap it in brackets to say negative 2. Yeah, the issue is that you're trying to do multiplication and then subtraction, whereas if you put brackets around it, it knows it to be negative 2. Make the math wrong? 4 times negative 2, 8. Whatever. Yeah, so 8, negative 8 would be 3 minus negative 8. Oh, that's why. Okay, I did plus. Right. So that's that one. Let's do another one here. Lucky 725 equals lucky x comma y. Z is x plus y times 2. So we've seen all of these things, maybe not in this structure, but the pattern doesn't, the way we apply the rules doesn't change here. So the pattern's still the same there. So we start left to right. We say, will these two things unify? We have two compound terms. They have the same functor. They have the same arity. So far, so good. And we go through step by step unifying the individual arguments. So 7 unifies with x, unbound, so that's fine. And 25 unifies with y, which is again unbound, so that's fine. So now we have the unifier x equals 7, y equals 25. And then we ask this math here. Z is x plus y times 2. So y is 25, times 2 is 50, plus 7 should be 57. So x is 7, y is 25, z is 57. So just unify and then some math. Okay, so the way we create these variables can still be used elsewhere. We can do them with compound terms. We can do them with literals as we've done them before. All right, let's do a more involved one. X equals 25 times 50.5. Y is 25 plus 50.5. X equals y. Actually, I'm going to change this. Obviously, that's going to be different because we have times versus multiplication. If I do it like this, true or false. So let's walk through this again now. So x equals 25 plus 50.5. So again, remember with the equal sign, we're just saying unify with whatever is on the right-hand side. It doesn't say evaluate at all. So it just takes this as the compound term. So plus 25 comma 50.5 as x. So x is now a compound term that happens to have 25 and 50 and the plus symbol. And y is 25 plus 50.5. So is says evaluate this, so that's 75.5. So y is now 75.5. X is a compound term. So compound term equals a number. Those don't unify, so we get false. Right. Again, if I just type this in, x equals 25 plus 50.5, that's what x is. It's not evaluating something, whereas y is 25 plus 50.5 says do the actual math. Now those two terms obviously won't unify, so we get false. All right, next one. 5 is a minus b. A equals 10. B is 5. So again, true or false, will this unify? We start on the left and say 5 is a minus b. So is means evaluate the right-hand side, and we get a minus b. What is the value of a minus b? Well, we can't really answer that because a and b don't have values yet, right? We want them to be a equals 10 and b equals 5, but that hasn't happened yet because it goes left to right. So we have uninstantiated variables when we're trying to do the is operator, so error. Let's do another one then. If we wanted to fix that one, we could just rearrange some of these terms. So we could say a equals 10, b is 5, and then 5 is a minus b. Now we do the unification a to 10. We say b is 5, which does the evaluation, but there's nothing to evaluate, so 5 just has its own value. And then the unification. So an extra step, but still the same result. So a is 10, b is 5, and then we have 5 is a minus b. So we have 10 minus 5, which gives us 5. Unify 5 with 5. That's easy to do, so true. And we get our unifier. All right, and how about this last one? Foo 3a equals foo b3. Y is minus ab. X is 100 divided by y. So we walk through it. And the first thing we have is the compound term. So same functor, same arity. Will the individual terms unify? We have 3 with the unbound variable b. Sure. And we have a with 3. Sure. So a and b are both 3. Not a trouble. And then we have minus ab. So if we have the is operator, even with a prefix notation, it's still going to do that subtraction. So we get 3 minus 3, which is 0. and now y is 0, and we have x is 100 divided by 0, which obviously should give us an error, and Prolog crashes 0 divisor. Yeah. Okay, so that's some practice with Prolog arithmetic, and just remember the general idea for Prolog is if you're just using the equal sign, it's not going to evaluate anything. If you use is, or this other operator up here, which doesn't really have a great name, you can evaluate both the right side or both the right and left hand side, depending on your operator. So make sure you're using the correct operator if you want the arithmetic to actually take place. Okay, let's do a slightly bigger example then with some rules here. I'm going to make a new demo here. New text document. Let's call it arithmetic.pl. Okay, and we'll open that with Notepad. Oh, what just happened there? We will open that with Notepad. There it goes. And then we can type in some rules. So I'm going to write some rules, and then we'll see some queries, and we'll try and decide whether or not these queries should give us true or false and what the unifier should be. So some simple rules, nothing that makes any sense, just some practice with unification and arithmetic rules in Prolog. So n is equal to or less than 10. Another rule is red and n if n is equal to 2. And blue and n if x is n times 10 minus 18 and x is greater than or equal to 5. I'm just going to change the language here to Prolog so it's all one color. So those are our rules. Pretty meaningless rules, but again, that highlights the fact that Prolog isn't doing anything semantically. It's just matching pattern to patterns. So we should do the same if we're trying to understand this. So I'm just going to put this to the side. We'll open up arithmetic in the Prolog window, get everything together. Oh, that was the wrong one. There we go. Get everything together. And then let's do some queries. So again, I recommend pausing between each query just to see if you would understand what you expect Prolog to do before you see what Prolog actually does. So our first query, good, given green and 7. So the question is this true or false? Now we don't have an equal sign in here, so the unification is between our query and something in the knowledge base, specifically the heads of one of these rules. So good, green, 7. We have the functor good with arity 2. So we have the functor good, and all of these have arity 2. So this could unify with any of these rules. It will do so with the first one first, though. And then specifically, we have the constant green as the first argument. And that will only match one of these rules, because we have constants in our rule heads here, where we have green, red, and blue. Since I passed in green, then I'm essentially specifically selecting this rule. And I'm providing the value 7 for n, right? So the unification says same functor, same arity, then go 1 to 1, so green matches with green, 7 matches with n, where n gets the value 7. And then we go into the body, and this also needs to be true in order for the entire thing to be true. Now if n has the value 7, 7 is less than or equal to 10, so that's true, so the whole thing comes out true. Okay. Similarly, we could ask good with red and 2. And again, this will unify with one of these rules. It'll start to unify with this first one, right, because it has the functor good and the arity of 2. But then it tries to unify the first argument green with our first argument red, and those don't match because we have two constants that are different. So it backtracks and says, well, maybe there's a different good. And there's one good here that has the functor good and arity 2. And the first argument's red, so that's great. Then we have an unbound variable n for a number 2. So that will unify with the head and says this is all true now if the body can be proven true. And now since we've unified n with 2, the scope of this binding is the rest of that clause, so this one line. So if n is 2 in the head, n is 2 throughout the body as well. So we have 2 equals 2, that's true. Okay, let's do one other one. Good, blue, 1. So good blue 1. So again, it won't match the first two because the constants won't match, but good blue here, where n is 1. So then we walk through the body of this rule where n is bound to 1. So x is the result of this calculation. So if that's 1, we get 1 times 10. Minus 18 should be negative 8. So x is negative 8. Negative 8 is greater than 5. That's false. So this should come back false. Right, so it unified with the head fine, but we couldn't prove the body to be true. There's no other good blues that it could have unified with, so the whole thing comes back false. Let's see here. Let's do a true one as well. So good blue 3. So again, that matches to here where n is 3. We walk through, we get 3 times 10 is 30. Minus 18 should be 12, so x is 12. 12 is greater than 5 is true, so we get true. Now, in all of these queries, we provided a constant that would match with just one of these rules, but we could also say something like good some variable, and then let's provide a number still. We could also provide a variable there, but that might break things. So we have a constant, or we have a variable c here that matches with the constants in our rules. So this will unify with the first case, right? We have the functor good arity 2. Green will unify with an unbound variable c, where c gets that value. And the unbound variable n will unify with 8, where n now equals 8. So coming into the body of that rule, we have n equals 8. 8 is less than or equal to 10. That's true. So this will return true if c equals green. But it didn't try the other rules, so it's sitting here waiting for me to ask, should we backtrack? So let's try these other rules. Okay, so we backtrack, we unbind everything and say, what happens if we try using this second rule instead? So the unbound variable c will unify with red, and n will bind with 8. So that's fine, that'll unify. And it's true if we can also prove the body to be true. In this case, n is 8. 8 does not equal 2, so that's false, so that won't work. It'll backtrack again and try a different version here, and say, what if c is blue? Okay, that's cool. N can still be 8, and then we'll walk through the body of this rule. So we get 8 times 10, which is 80, minus 18, which should be 62. 62 is greater than 5, so that should be fine, and we get true. So if I backtrack, it's also true if c is blue. Okay, so we can use these rules in different ways is the point there, and just to walk through and understand how every piece unifies. All right, anything else we want to do? Right, let's do this one. So let's do good green with a variable here. So this will only unify with one of our rules because we only have one rule where the first argument's green. We have the variable n binding with the variable n. Now these are technically different n's, and maybe I should use a different term here. It actually doesn't really matter. But if I change this to, let's say, x, now we have the unbound variable x binding with the unbound variable n, which is fine. What that means is if this variable ever gets a value, then x will also get that value. If one of them gets a value, then all of the unified variables will as well. But what actually happens in practice, the head unifies, we go in to prove the body, but n is unbound, and we're asking, is n less than or equal to 10? We can't do a comparison operation on an unbound variable, so then this one crashes. Okay. Let's do a similar one with blue. Good blue n. So again, this will match the head of our rule fine, right? It's almost identical, where we have the unbound variable n unified to this unbound variable n. We go walking through here and we say this first clause. X is the result of calculating this math, where the first step in that math is multiply n by 10. But we didn't pass in a value, so we can't multiply an unbound variable by 10, and we get a similar error, uninstantiated values. Let's try red though. Good red n. So if history is any indication, this should crash as well, but let's walk through it. So again, functor good arity 2, where the first argument is red, so that will unify with the head of this rule, right? Good red n, where this unbound variable n, or let's just call it y for the sake of argument, just so we have two different variable names. So this unbound variable y will unify with the unbound variable n. So kind of somewhere in the background of Prolog, it remembers that y equals n. Okay, and then it goes in to try and prove the body, and it says n equals 2. Now this equals operator, we remember before, is essentially just does unification. n is still an unbound variable. It's bound to another unbound variable, but that just means you have two unbound variables, or a chain of unbound variables. So what happens here when we say n equals 2, we assign the value of 2 to the variable n, which assigns the value of 2 to the variable n throughout this clause. And because we said y equals n, it also assigns the value of 2 to the variable y. So if we hit enter, we get true with y equals 2. Okay? So sometimes it's okay to pass in unbound variables. The only times that it's really not safe to do so is if you're doing comparison or arithmetic on them. Those need instantiated values. But if you're just doing unification, it's almost easier to do unification if you have unbound variables. Okay, let's do one last one here. Good, red, blue. So will this unify? So we have the functor good, that's great. We have the arity 2, that's great. The first argument is red, so that won't match this because green won't unify with red. But red will, so red unifies with red. And then the second argument is will blue unify with n? Okay, there's no problem there. We have the variable n unifying with blue. But then we go into the body of red and say blue equals 2. And that's obviously not true because we have an atom unifying with an integer. So those aren't the same thing, and we get false. All right, so that's it for arithmetic. Let's move on to the one last set of operators, and that's basic I/O. Where are my notes? Just dig through these windows. There we go. So some basic I/O operations. So there's reading, writing, and just printing the new line are the important ones here. So let's start with, is this the one we're using? I don't think it actually matters. Oh, that's the one with the rules. Okay. Yeah, it doesn't actually matter. We're just typing things into the Prolog interpreter. So the write operation just does printing to the console. So I could say things like write 1 + 1, for example, and it just writes 1 + 1 and then returns true. So it's useful for debugging. For example, if you have some large system, you want to print out something that's happening in the middle of that system, you can just use the write operation. If you want to have a new line in there, so write hello, and then new line, writes hello, and then puts multiple new lines so we can actually see it. There you go. Some new lines in there. Okay. So that's those. There are some other useful things for printing out internal representations, right? There's a display 1 + 1, which prints it out a little bit differently. Instead of writing exactly what we shows, it prints out the internal representation instead. Don't worry too much about that. Writing is pretty much only used for debugging in this course, at least. And there's also the reading, so we can read user input as well. So I could say something like write enter a number, and then read some variable x from the user. Since I asked them for a number, I'll assume they did nicely, or they played nicely and gave us a number. And we'll say y is x + 3. And we can write x + 3 is new line, and then y. So we run this. It writes out enter a number, and then notice it pauses at the read. So let's put in a value 5, hit enter. Oh, sorry, enter full stop and then an enter. And then it says 5 + 3 is 8. So it put the 5 that I typed into x, then did the remaining math that we've already seen, writes out x, writes out some labels, new line, and then y. Okay. And that's about it. So those are the basic Prolog operations. You should make sure you understand them all because they're the components that you're going to be using to build up the many rules that we're going to start making in the coming lectures. So talk to you next video.